Hi, everybody. Welcome to the fourth seminar. Thanks for joining us today. Today we'll have Marc Hirschmann talking to us about the deep earth oxygen cycle. First, I'd like to introduce myself. My name is Kara Brugman. I'm a research scientist and the outreach coordinator for FORCE.
And my name is Kyusei Tsuno. I'm also the research scientist over the FORCE.
First, I do want to remind you that you can see videos of our previous seminars with Matt Whitaker, Sally June Tracy, Ben Chen, Yingwei Fei, Tim Officer, and Jin Zhang on YouTube. The video of this seminar will be posted in the next couple of weeks. You can sign up for the listserv at force.asu.edu/newsletter to get updates, or you can also subscribe at our YouTube channel, bit.ly/forceyoutube. We have 3 more seminars this semester, and Pommier, Andy Campbell, and Innocent Isenwa will be speaking to us in the coming months. And I wanted to give you a little bit of a recap. We had our winter workshop in January. It was a great success. We had a great group of people. And we were also able, because of our generous sponsorship, to give some cash awards to some students for outstanding poster presentations and also to support their travel. Thanks to Corning for that, and thanks to everyone who came. Also, you can go to our website on the front page or to bit.ly/forceprogress 2024-216 to download our latest progress update, which also has an updated timeline of our press delivery schedule and when the construction phases will be complete. Right now, phase 1 is complete. We have our temporary certificate of occupancy, and we also have been giving some tours inside the lab. This is our research technician, Logan Leinbach, giving a tour to some of the School of Earth and Space Exploration prospective graduate students. And we also received our first shipment of our 52 millimeter carbide for Ichiban. The rest will be delivered at the end of this month. And probably most exciting is that this week we did our first solo compression test of Ichiban. This is the lab staff team standing in front of Ichiban himself and Kurt pushing the button to start the auto pressurization for Ichiban for the first time. It's a really exciting time at the lab, and we're really excited to start going on getting the experiments assembled and start doing all of our calibrations so we can serve our users soon in the coming years. All right, with that, I'll turn it over to Kisei.
So it's a great honor to have Professor Marc Hirschmann at the University of Minnesota Twin Cities, working for more than 25 years, and he is now designated as a magnet professor of the Earth Science Department. So he's an experimental and theoretical petrologist and geochemist whose work elucidates the early differentiation and the redox evolution of the rocky planets and the cycling of life essential volatiles such as carbon, water, nitrogen, and he will be talking about the oxygen. And from the past to present, and from the exosphere to the center of the planet. In other words, each layer or lithology such as atmosphere, crust, silicate mantle, and the metallic core. So today he will be talking about the deep Earth oxygen cycle. So time is all for you.
Thank you, Kyusei and Kara for the introduction and for the invitation, and thank you everybody for showing up. Let's see if we can get things going here. Okay, are we good? Excellent.
Yep.
Okay, so my topic today is something that I call the deep earth oxygen cycle. It's actually kind of a polemic in a way to try to get the large community of people who work on redox in the mantle and work on redox in planetary interiors to think about things a little bit differently in a way that, first of all, better engages the interactions between the interior and the surface, and second of all, gets us out of the hole that many of us fall into in talking about only about oxygen fugacity, which is something that people find quite puzzling, and moving it towards mass balance, which helps us with understand it in somewhat of a different way. Because this is a FORCE seminar, and because, before I say that, I should point out that there's really important collaborators involved in this, most importantly, Hanglo Zhang, who was once upon a time my PhD student, but now she's faculty at Chinese University of Geosciences in Beijing. And much of the experimental work that I'll be presenting is her efforts. And then she and I have a whole bunch of other collaborators who have helped us along the way. One thing you might note about this list of names, it includes Oliver Lord, Mike Walter, Liz Cottrell. But these are three people who, in addition to Hong Lo, have a lot of experience with the experimental technique that I'll be talking about, which is diamond anvil experiments. Those of you who know me will know that I am not a diamond anvil experimentalist, and the key new experimental data that I'll be presenting has been done very much in collaboration with other people rather than coming out of my own lab or even coming out of my own expertise. So again, because this is a 4th seminar, I was asked to sort of say a little bit about the techniques that I'll be using and also the context. In fact, a huge portion of the talk will be context, but I just want to point out that indeed the experimental data, which come in the second portion of the talk, actually come from diamond anvil experiments, laser heated diamond anvil experiments, which I think many people know are the way that we get to very extreme temperatures and pressures that probe the interior, the deep interior of terrestrial planets. And so we can get to very high temperatures and very high pressures in doing that. The limitation, of course, is a spatial limitation. The actual size of the pressurized region is usually less than 100 microns across. And then when we're laser heating, the actual heated region is something on the order of 20 or 30 microns across. And for a mineral physics tool, this has been extremely useful, but for an experimental petrology tool, it is much more problematic because normally in experimental petrology, what we want to do is not simply have a single phase where we're probing its physical or chemical properties, but rather phases that are coexisting and hopefully perhaps even something like approaching equilibrium. And at that spatial scale, first of all, that is difficult. And second of all, once one has done so, characterizing the individual phases by whatever spectroscopic or microbeam techniques is also quite challenging. So we'll return to diamond anvil experiments, like I said, in the second half of the talk, but let's zoom out and think about oxygen and redox on terrestrial planets in general, and more specifically on Earth. Before we delve into the mantle, it's important from my perspective to point out that surface redox dynamics are key to almost everything about surface geology. Certainly, global biogeochemical cycles are the coupled cycling of oxygen and sulfur and carbon and other redox-sensitive elements on the surface. And there are mass balances and fluxes that have been enumerated by many people that I think we should be paying attention to. Also, I think it's become a very prominent problem in the last 15 or 20 years in the earth science community, trying to understand the evolution of surface redox dynamics. This is known as the Great Oxygenation Event. And this is something that has been sufficiently appealing that earth scientists interested in the solid earth have wanted in and have wanted to point out the role of the interior in this evolution of Earth's surface redox dynamics. So this is just a bunch of headlines of different papers arguing actually from multiple different perspectives about the role of the deep Earth in surface redox evolution. And I'm going to argue that, yes, this is actually important, but in order to do this, we're going to need to translate the way that we think about things in the interior of the Earth to the way people think about things on the surface. So like I said, on the surface redox, people tend to think about mass balances and fluxes. And on the left is a very classic sort of box geochemical model known as BLAG, carbon, sulfur, oxygen cycle. And again, all of this is mass transfer. Whereas for the most part, in the mantle, we think about things like oxygen fugacity. And so on the right is a plot inferred from oxybarometers of the evolution of the mantle with time in redox state, but the redox state is quantified in terms of something called oxygen fugacity. We need a way to go back and forth between oxygen fugacity and mass balance if we actually want to think about what's going on in the surface and its relationship to the interior. I will definitely be returning to that plot on the right several times and saying more about it, but I'll leave it at that for the moment. A second thing that we want to address is the fact that there's so much redox or oxidative power in the Earth in the first place. It is not necessarily something one would assume from a cosmochemical perspective. Earth's ingredients, Earth's building blocks, chondrites or things like chondrites, are silicate coexisting with metal, and as a consequence, they're quite reduced. On the other hand, when we look at Earth's interior, and this is true going all the way back as far as we can see into the Hadean, is considerably more oxidized than those building blocks, and therefore has much more oxidative power. All the oxygenation on the surface exists by permission and by fluxes from the interior, but the whole thing starts with an oxidized mantle of a planet, and it's even actually more oxidized on Mars than the cosmochemical building blocks as well. So the origin of Earth's oxidative power is an important part, and that's actually the part where we'll get to experiments. And then also, I want to emphasize again that there's some evidence that the Earth's mantle has evolved in oxidation state through time, not necessarily accepted by everybody, but there's some evidence. Whereas we know that it has been comparatively oxidized compared to chondrites, compared to equilibrium with metal since the very beginning. And the general picture of this has been something like this. On the left is basically that same plot that I showed you a moment ago that shows something like 6 orders of magnitude of change in this parameter of oxygen fugacity from the birth of the cosmochemical materials to the earliest mantle. And then perhaps in the last 2.5 to 3.5 billion years, an evolution that is small, controversial, and much different in magnitude from that original so-called great mantle oxidation event. Maybe a log unit or a log unit and a half of evolution. On the other hand, that is in this parameter space, oxygen fugacity, that doesn't necessarily tell us what sort of mass balances are required to affect this kind of change. So that's something else that we want to address, that I want to address. I worked for something like 20 years on things that are known as deep earth volatile cycles, and I think many of you have also worked on deep earth volatile cycles of one sort or another. In terms of deep earth science and experimental science, it's been an extremely fertile way to understand not just the volatiles themselves, but the chemical geodynamics of terrestrial planets. And so we think about the deep earth volatile cycles of hydrogen or carbon or nitrogen or sulfur. And the properties of a deep earth volatile cycle is that these materials have dynamical properties both on the surface and the interior. They are represented by large reservoirs in both the interior and the surface, long time scales of exchange between them. And the dynamics of the solid interior and the surface are important, right? So the most familiar one probably is that the more water there is in the mantle, the lower its viscosity, the more it convects, the greater the fluxes of water out of the mantle, and so on. The reason that I talk about the deep earth oxygen cycle, even though I could be calling it the deep earth redox cycle, but I do want to associate it with a particular element, is that, in fact, all of those properties apply to redox circulation dynamics as well. And so the context of deep earth volatile cycles and the way that we have previously approach those can also be approached for oxygen. Just to quickly digress to examples, the physical effects of redox on mantle properties are several, but here are 2 really good examples. One is that redox affects the locus of melting on a relatively oxidized planet such as Earth. In the shallow mantle, the carbon exists as carbonate, and we know that carbonate is an excellent flux for expanding the region where partial melting may occur. On Mars, which is more reduced, for example, and may have graphite in the source region of Martian basalts, that means that comparatively the locus of melting is smaller. Similarly, the physical properties are affected by redox. So something like rheology, olivine creep, this is a study from about a dozen years ago from here in the University of Minnesota in David Kolsted's lab, showing that the strength of the mantle, in fact, and its rheology depends on oxygen fugacity as well. So the way that I'm going to approach mass balance in the interior and also on the surface is something known as the redox budget, which is abbreviated RB. And RB was invented by Katie Evans about a dozen years ago, and she was using it to quantify fluxes in subduction zones. And I'm basically going to lift her methodology and lift her terminology almost directly, except for that I'm applying it to the entire bulk silicate earth, where she was focused chiefly on subduction zones. And the redox budget is an extensive property. It is the number of moles of electrons that are required to take an element or a store of elements from their present state to a reference state. And the reference state that I take is that of the principal redox state of each of the elements in the mantle. So for the iron, that would be Fe2+, for sulfur, that's S2-, and so forth. And the way that works is that a species more oxidized than the reference state has a positive RB, and a reduced species has a negative RB. And with that context, we can start just with the surface and take what many people have done over a long period of time of quantifying the different oxidative budgets on the surface. And what we find is that the Earth's exosphere redox budget is composed chiefly of these different constituents. Notice that this is a log scale, and notice that if we sum up all the oxygen in the atmosphere, it's dwarfed by the more condensed oxidized species. It's dwarfed by the sulfate, which is in turn dwarfed by the ferric iron in the crust, which is in turn dwarfed by the carbonate. And you may not always think about carbonate on the surface as being an oxidized species, but the key point here is that relative to its principal redox state in most of the mantle, which is reduced carbon, graphite, diamond, carbide, and so forth, the carbonate is oxidized. So that's a number, the total amount of moles of redox budget in the entire exosphere. And for those of you who aren't familiar, when I say exosphere, I mean basically everything above the MOHO, the crust and above, the crust and the fluid envelopes. The redox budget of the mantle is dominated by the small amount of iron in the mantle that is ferric rather than ferrous. And there are different estimates of that. And actually, in fact, I think we could do a pretty good job. We could do a better job than we have of estimating that. But people based on peridotites or based on inverse modeling of the amount of ferric iron in basalts come to the conclusion that something like 4% of the iron in the upper mantle is ferric rather than ferrous. So the number that I'm going to take for that is 0.04 plus or minus 0.01. Perhaps we could do better with that number. But if we do that, we get a redox budget that's shown on the bottom there, which without any context doesn't have much meaning for you yet, but I will show you a little bit more about it in a moment. All the other redox-sensitive species in the mantle are small in their contribution to the RB compared to the ferric iron. So we can think about that portion of the mantle that has carbonate rather than carbon. I'm not going to show you, but we can also think about the fact that the sulfide isn't exactly S2-, and that not all the chromium is chromium 3+. And we end up with values like this, and it's all dwarfed by the ferric iron. So now we have the redox budget of the interior and the surface. And what we see is that about 80%, 4/5 of the entire Earth's redox budget is in the mantle, and only about 20% is on the surface. And when I give this talk or versions of this talk various places, I tend to ask the audience. It's not a very good interactive environment in Zoom. You know, does this surprise you? And most people aren't surprised by it, but I found it fairly surprising. And the reason is because these things that are oxidized in the mantle are incompatible. They're things that the mantle wants to get rid of, and yet it has kept 80% of it. And there's an echo there. And that echo is the same as that of carbon in the Earth, which is that even though carbon is incompatible and wants to go into melt and therefore is easily shed from the mantle and brought to the surface, most of the carbon in the accessible Earth is in the mantle. And this pairing between carbon and oxygen is actually a theme that will continue for the next 15 or 20 minutes. Okay, that was my introduction. Now, from that introduction, I have 3 chapters that I'm going to continue with, three questions that I'm going to address or to try to illuminate. The first is, now that we know what the reservoirs are, what are the fluxes? How are they expressed, and what's their vigor through time? The second is this thing that I already brought up that has to do with the scaling between oxygen fugacity, which is an expression of chemical potential and not that accessible to many communities, and actual mass balance. And then the third, which is the one that brings in the experiments, is what's the origin of all this large redox budget in the accessible Earth in the first place? I think that deep Earth oxygen cycles invite a whole bunch of other questions that I'm not going to address. I invite you to address them, and they're listed here. All really good problems and things that people have indeed worked on, but I think can coalesce better within the context of this framework, just as things that people worked on having to do with water were better framed in terms of the deep Earth water cycle, or carbon best framed in terms of these large-scale investigations of the deep Earth carbon cycle. Okay, so chapter 1, the fluxes. We can sum up all of the fluxes coming out at ridges and at oceanic islands and other intraplate boundaries, and they look like this, and I've taken them from the literature, and they give us a number, and I'll return to the number in the first in a moment. But a really interesting thing is that the messenger, the redox flux coming out of the mantle, is dominated by CO2. Most of the oxidized flux out of the mantle is CO2. We also care about the subduction fluxes or the return fluxes of oxidized species to the interior. And this is a really large topic that deserves a lot of re-examination based on new data, which I have not done. What I have done is I've taken Katie Evans' work that I mentioned earlier from a dozen years ago for the global subduction flux, redox budget subduction flux. And all I've done is tweak it a little bit by pointing out and taking note of the great G-plates work that's been done since then, that first of all shows that the rate of subduction has not been constant, and instead of having the modern rate that Katie Evans used, I'm using the average 200 million year rate from basically from the last couple 100 million years. And also that the amount of carbonate and the amount of sediment that is subducting right now is kind of anomalously high compared to that 200 million year average. And so I'm using the 200 million year average for the different components of what's actually coming in on the plates. And so this gives the influxes, the redox budget subduction influxes, averaged over 200 million years. And it's a number. Again, I'll highlight what that number is. But the important thing here is that the messenger going in is ferric iron. The messenger coming out is carbonate or CO2, and the messenger going in is principally ferric iron. This slide summarizes what the reservoirs are and what the fluxes are, and we can look at the mantle outfluxes and the subduction influxes, and we can look at those numbers. Within uncertainty, they are not distinguishable. Within uncertainty, we cannot say whether or not the surface is gaining redox power or whether or not there is more redox power presently going into the mantle. If we could resolve those uncertainties, it might actually be that at the moment, the redox power is flowing back into the mantle, but we don't have enough resolution to say that at the present time. But again, the key thing is look at the blue up above versus the red below. It's carbonate coming out, and it's ferric iron going in. The redox mass balance, the deep Earth oxygen cycle, in its most basic form, can be summarized by these basic conjugate reactions. Most of the redox power in the mantle is ferric iron, but some of that ferric iron converts to carbonate in the shallow mantle, as illustrated in the center lower portion. And that's the part that's coming out. So one key conjugate reaction is redox melting, forming carbonate in the shallow mantle. On the surface, that carbonate is converted to oxygen, basically by photosynthesis. Isn't it interesting that the key cycling or the fundamental cycling of the entire accessible Earth involves biology? And then that oxygen is converts ferrous iron to ferric iron by oxidative weathering. And so in the mantle, ferric iron to carbonate; on the surface, carbonate to ferric iron. And this is what balances or approximately balances the redox cycling on Earth. If we look at those fluxes in terms of the size of the reservoirs, we can say how long it takes for the surface redox budget to cycle through the mantle. And what we get is a characteristic cycling time of approximately 1 billion years. In other words, this entire surface reservoir on the ferric iron, the carbonates, and so forth, they are cycling through the mantle multiple times over the history of Earth if current rates are applicable going back. And it's a dynamic system that is setting this. And that, again, is true of carbon as well, but probably not true of water and nitrogen. Water and nitrogen have such large cycling times that the initial budget of water and nitrogen on the surface, initial meaning, I don't know what I mean by initial, first few 100 million years, I guess, that they haven't changed a large amount since then, whereas carbon and oxygen are regulated by the plate tectonic system or by the tectonic system on a billion-year timescale. Okay, chapter 2, redox scaling and the magnitude of possible mantle secular evolution. So I showed this plot before, and now is the point where I need to clarify. The evidence for secular evolution of redox changes in the mantle depends on trace element oxybarometers that are under dispute. And what I'm going to do in this talk is not talk about whether or not this is true or not. I'm going to talk about what it means if it is true. So if we accept the redox oxybarometers as accurately reflecting something like a log unit or a log unit and a half of secular evolution of Earth's mantle since the early Archean, then what are the consequences for that? Or another way to say that is, how much mass transfer is required to do that? And again, the picture that we have from just oxygen fugacity is that the mantle was very oxidized compared to its building blocks, 6 orders of magnitude or thereabouts at the very beginning, and then a small adjustment ever since then. Does that really hold up in terms of mass balance? So we want to translate the oxygen fugacities in the mantle to mass balance. And this is actually not that difficult, and other people have done it for other contexts, but not applied it in this particular way. And the way that we want to do this is to say for a parcel of mantle with a given redox budget, which is, in other words, is a given amount of ferric iron, how does the change in ferric iron in the peridotite influence the change in oxygen fugacity that peridotite will reflect if we apply an oxybarometer, or the redox of the basalt that peridotite would make when it partially melts? And so I do this sort of in 2 parts. One is an empirical part and another is a thermodynamic part. The empirical part is to simply say, if we have a certain amount of ferric iron in the peridotite, what is the ferric iron in each of its constituent phases? How much ferric iron is in the pyroxene? How much is in the spinel? Or if it's in the garnet facies, how much is in the garnet? And so this just simply comes from empirical partition coefficients. And once we have the ferric iron in each of the constituent phases, we can use thermodynamic models to calculate the oxygen fugacity by writing reactions similar to the one on the lower right there. Orthopyroxene plus magnetite and spinel goes to olivine and oxygen. These are very well-developed oxybarometers. Depending on the conditions that we assume, spinel peridotite versus garnet peridotite, higher temperature, lower temperature, higher pressure, lower pressure, the absolute value of these varies a lot. But what doesn't vary is that the slope on a plot of QF delta QFM, or any oxygen fugacity indicator, which is a logarithmic indication of oxygen fugacity, is linear with respect to the logarithmic content of the ferric iron content of the peridotite, and it has a slope of 1/4. And that slope of 1/4 is based on that reaction that I have highlighted in the plot there of FeO plus 1/4 O2 goes to FeO 1.5. So we get the scaling slope, and that's what we care about in order to quantify oxygen fugacity in terms of mass balance. Okay, so I've already shown you this. Let's take a different look at this plot on the right and add the mass balance in. And that's what it looks like on the right. So if we say that the mantle at present has 0.04 ferric over total, and previously it was a log-and-a-half unit more reduced, what we find is that the mantle ferric over total was less than half it is at present. In other words, if we go back into the Archean and say the mantle was a log unit and a half more reduced than it is at present, then it had half of, or at least the part that was sampled in rocks, sampled in peridotites, and sampled in basalts or eclogites or whatever we get from komatiites and so on, coming from a mantle that was in mass balance much less oxidized than the present mass. More than half of that redox budget has to come from somewhere. Just to give you a scale of that, right? If remember, we have something like 20% of the redox budget on the surface. If we were to take all of that redox budget and mix it back into the mantle and recycle it back into the mantle and mix it very well into the mantle, we would get something like less than half a log unit change in the entire mantle, right? So in order to move the mantle around a half a log unit, and so forth from its present state requires really large fluxes of redox species from somewhere. It's been suggested that this could be from hydrogen escape. The problem with hydrogen escape is not that from the atmosphere, is not that this can't happen, but it's very, very hard to get the fluxes from the surface into the interior. It's very hard to do that. It would require subduction fluxes, something like an order of magnitude or a factor of 20 greater than they are today in an environment where there isn't a great deal of carbonate or a great deal of ferric iron on surface rocks and so forth. So that's very hard to do. There's a number of papers that have been written in the last few years that suggest that what really was going on was that the mantle was redox stratified for its first several billion years. And that redox stratification resulted from its early differentiation. And it took a couple of billion years for the more oxidized portion to be expressed in the upper mantle and therefore to be sampled in basalts and komatiites and peridotites and so forth. And I have to admit that when I first saw these papers, I thought they were crazy, but a light bulb went on when I realized that what was being argued was really analogous to what we actually see in the isotope record. In the isotope record, we see that, and this is illustrated in the plot in the lower right for neodymium-142, we see that really ancient rocks reflect really strong mantle heterogeneity up until about 2.5 billion years ago, where finally the mixing of the lower mantle and upper mantle became efficient enough so that pretty much everything that we sample in the mantle today has the same neodymium-142 ratio. So this is actually plausible if, right? It's plausible if, first of all, there was this redox stratification, and if the mixing between that deep region and the surface was expressed in mass balance the same way it was expressed in isotopes. So that would look something like this, moving from right to left in this diagram. Oh, excuse me, moving from left to right, yeah. Which would be that initially a great deal of oxygenated power originated by whatever process. I haven't told you my favorite process yet, but it could either be in a magma ocean or Bridgmanite crystallization or hydrogen escape. Doesn't really matter. Then at some point, that material has a preferentially oxidized region in the deep mantle. And then subsequent to that, that mixes in over the first half of Earth's history, over the first 2 billion years of Earth's history. That's not necessarily right, but if in fact Earth's oxygen fugacity, Earth's mantle oxygen fugacity is evolved by as little as a log unit or a log unit and a half, something that fundamental in terms of mass balance and mixing is required. The small changes in oxygen fugacity that are inferred from the rock record, if they're accurate, reflect really big changes in mass balance. Okay, chapter 3. Where does all this oxidative power come from? There are 3 ideas for this great mantle, great oxygenation event that translated the building block materials that were reduced and in equilibrium with iron to the upper mantle and the well-mixed mantle that we have today, that's orders of magnitude more oxidized in terms of oxygen fugacity. One of those ideas is that it's hydrogen escape, that it's water disproportionation in the atmosphere making hydrogen, which then escapes, and the remnant oxygen then recombines with iron to make, with ferrous iron to make ferric iron, and that is the birth of the oxidative power. Another idea that actually originates with Dave Mao a long time ago, but was popularized chiefly by Dan Frost and his colleagues at Bayreuth, is that mantle minerals, and in particular bridgmanite, are so stabilizing of ferric iron that when they crystallize in the lower mantle, they force disproportionation to make ferric iron and iron metal. The iron metal later is removed to the core, and what's left behind is an oxidized mantle. And the third idea, which is quite similar to the second idea, but there's an important difference, is that disproportionation happens not because of crystallization of bridgmanite, but simply because silicate melts at high pressure also may stabilize ferric iron and force that disproportionation and force additional metal to be shed to the core and leave behind an oxidized silicate reservoir. This is something that I suggested about a dozen years ago, and it was sheerly speculation. There was actually no experimental evidence for it. And subsequent to that, people have sought experimental evidence for it, and that's really what the rest of my talk is about. What was known at the time about the thermodynamics of ferrous and ferric iron in silicate melts was the opposite of what I told you for minerals, which is to say that rather than ferric iron being stabilized at high pressure, from the low pressure measurements we had at the time, ferrous iron was stabilized by pressure. And that's reflected in this diagram. Can you see my pointer? Yes? Can you? Okay, good. That's reflected in this diagram here, where in a well-mixed magma ocean having the same ferric over total, based on what was known experimentally, that the well-mixed magma ocean would be more reduced at its surface and more oxidized in its interior at the same ferric ferrous. Whereas for solid peridotite, the constant ferric ferrous makes more reduced mantle, which is what we know to be the case for solid peridotite. So the speculation was that, I can point either to A and B in the shallow mantle. The speculation was that this trend, known from silicate melts at low pressure, would reverse and take the same slope or something similar to the same slope as peridotite, in which case a deep magma ocean would stabilize ferric iron in equilibrium with iron metal and make an oxidized mantle. Of course, this speculation led to our attempt to prove it experimentally. And this actually, I introduced Honglo Zhang earlier, and she's going to continue to visit us over the rest of this talk. Her PhD thesis was an experimental attempt to verify this. And I keep switching axes on you and things that I'm holding constant. So I'll guide you as to what this means. These experiments are buffered at the same redox buffer. It happens to be ruthenium oxide, but it doesn't really matter. The hypothesis that I proposed would be right if, with increasing pressure, the ferric iron over total at that buffer increased. And we did experiments up to 7 GPa, and we saw the opposite. It was a negative result. It suggested that what was known from lower pressure continued to be true at least up to 7 GPa. We stopped doing experiments at 7 GPa because above those pressures, and these experiments illustrated in the upper right were done in piston cylinder apparatuses and multi-anvil apparatuses. These experiments stopped quenching to glass. And because they stopped quenching to glass, we lost the ability to reliably, in our opinion, to reliably measure the ferric over ferrous in the quenched glasses. But other people took this up in different ways. And that includes the Bayreuth group, reflected in this paper by Armstrong et al. From 5 years ago. And the data here are actually our data and some earlier low pressure data, Hong Lo's data here. But the Bayreuth group went to higher pressure, and they saw this increase that we failed to see because they went to 23 GPa, whereas we went to 7 GPa. At the same time, and again, the axes are a little bit hard to follow. This is not experiments. These are molecular dynamics calculations done by Ji Deng, who's now at Princeton. And they show this reversal in the silicate melts from going, in this case, from more oxidized with increasing depth to more reduced with increasing depth. So experiments from this period of time, 2019, 2020, seem to verify the hypothesis that you can make and stabilize ferric iron in a magma ocean just from the high pressure properties of silicate melts. And then last year, another group said essentially the same thing. This is the Kuwahara paper. And they are stabilizing, in this case, with these experiments, silicate melt in equilibrium with iron metal that becomes more and more ferric iron rich with increasing pressure. So this appears to be like a direct analogy to what would be happening in a magma ocean. More and more ferric iron in equilibrium, in the silicate melt, in equilibrium with the core forming alloy. However, the reason that we have these experimental results is because these other groups went where we didn't want to go, which is to say, when they stopped quenching glass, they continued to do the analysis and continued to do the experiments and found ways to infer the ferric iron content from these quenched regions. And so if you see these plots here, these plots have filled symbols where the experiments quenched glass and open symbols where the experiments did not quench glass. And so the question remains as to whether or not this actually represents the ferric iron over total in the liquid, in the silicate liquid. Actually, long before any of this, because our experiments had started to fail to quench glass in the piston cylinder and the multi-anvil, we had begun a campaign of diamond anvil experiments that, in fact, we had not published, and to this day, we have not published. We're actually just about to submit the first paper on it now. And so these diamond anvil experiments were laser heating, silicate melt, coexisting with iron or an iron-rich alloy in the diamond anvil at extreme conditions, 30 to 70 GPa, something like 4,000 kelvins. And these were done at Bristol University, where Hong Lo went to work with Mike Walter and Ollie Lord. We started this a long time ago. The first experiments were done in 2014. And here's a micrograph. And I want to point out the scale of the scale bar here. This is just 10 microns. This is what was molten iron metal coexisting with silicate melt. It's actually a mafic glass, not an ultramafic glass. In the diamond anvil cell, or actually this is imaged, having been removed from the diamond anvil cell. We did not like these experiments. And the reason we didn't like these experiments is because in addition to the iron metal that we wanted to be there, there's iron metal distributed throughout the silicate. And we didn't know how to interpret that iron metal. And because of that, I'll show you what we did, but these experiments we did not and have not used to infer the stabilization of ferric iron in the silicate melt. This is actually a really common problem in diamond anvil experiments where people equilibrate alloy and silicate for reasons of partitioning. Distributed metal in the silicate is, I won't say ubiquitous, it maybe doesn't exist in every experiment, but it's extremely common. And that distributed metal, in order to actually analyze the silicate and say you know something about the silicate, you have to make some decisions, right? If it was created on quench, then your analysis of what was formerly the silicate melt needs some average of both the silicate and the metal. On the other hand, if it was present during heating, you need some way to analyze the glass without hitting those little bits of metal. And you can see the scale bars on these plots. They're tiny. The bits of metal are absolutely tiny. And so it's a real challenge. Our original experiments had iron metal coexisting with silicate. We decided to work instead with iron platinum alloy, to work with, which means that we were working at more oxidized conditions. And when we did so, we no longer saw the iron metal. I'll show you some micrographs in a moment. So these were done merely 7 and 8 years ago. It's a little bit embarrassing that it took us so long to get to this, but I'll explain why in a moment. Here are some micrographs of the charges that we will use, where platinum iron, molten platinum iron alloy was equilibrated with the glass. The 3 images on the lower right are ever more high resolution images of the glass, showing that we do not see metal at all in the glass. And therefore, if we can analyze the glass and if we can measure the ferric iron over ferrous iron, we're confident that we're measuring that of the melt and not of the melt plus metal, where we don't know the origin of the metal. We did Zane's analyses on these. We also did time synchrotron Mossbauer, time domain synchrotron Mossbauer spectroscopy on these at about this era. And we were not really confident that we understood the results for a host of reasons. For example, Zane's is a standard-based method, and when one measures the ferric over total, one needs standards. And we thought, what sort of standards would we use for glasses quenched from 50 GPa? They have a different structure from all the standards that we would otherwise have available to us. And therefore, we're not confident that inferring ferric over total based on low pressure glass standards would be relevant. A little bit more than a year ago, I was on sabbatical in Europe, and I had, through a combination of basically connections and persistence, we got access at ESRF, the beamline in Grenoble, France, to the energy domain Mossbauer spectroscopy system. And here's a whole bunch of the people involved in that trip, which happened last February, just about a year ago, and Hong Lo, who was again leading the work. And at ESRF, apart from the fact that we can see that the French know where to put their beamlines, please tell the Americans that that Brookhaven and Joliet, Illinois, are not on a par with Grenoble, just in terms of scenery. But the important thing is that there's, that there's energy domain Mossbauer, where one can put the beam down on a very small spatial scale. The beam during our analyses was something like 7 by 11 or 7 by 12 microns, and get a Mossbauer spectrum in just a couple of hours of time. And that Mossbauer spectrum can be analyzed and interpreted in almost exactly the same way, not exactly, but almost exactly the same way as conventional Mossbauer. And up here in the upper part are just showing a microprobe WDS element map showing the well-separated iron platinum alloy from the silicate melt. Notice that I showed experimental numbers there. It was like DAC 93, DAC 95. Hong Lo did a lot of experiments. I'm sorry to say, for all of the experiments that she did, we have 10 analyses that that we can use. Most of the experiments were failures. They produced metal. They didn't produce well-developed textures. Some of them were lost on polishing and so forth. So the efficiency of this was very low. And here are the actual results. We're not as reduced as we would be in equilibrium with iron metal, because the activity of iron in iron platinum alloy is far lower than it would be in the metal. But that's actually an advantage. That means that it enhances the ferric iron. Makes it easier to measure. This is out of place, so let's just go to here. If we take those results and fit them to a thermodynamic model that takes into account variations in composition based on low pressure work that many people have done, including myself, based the effects of temperature based on what we know about the heat capacity of ferric and ferrous iron, and fit an equation of state for the difference in volume between ferric and ferrous iron, then we can use our experiments to calculate the ferric iron over total in equilibrium with metal along a magma ocean adiabat. And that's what's shown there under fit 1. What is shown also is an earlier attempt that I made a couple of years ago based on similar data, except that it didn't include these new high pressure data. What's lower than that is the calculation based on molecular dynamics from Deng et al. And these two curves over here, the Kuwahara and Armstrong, are the equations of state that one gets from the experiments that were done in the multi-anvil, which appear to greatly overstabilize ferric iron. They are kind of too much of a good thing. If one speculates that a deep magma ocean should stabilize ferric iron, those experimental results suggest so much ferric iron stabilized in a magma ocean of the depth that we think that Earth's magma ocean, mean depth that Earth's magma ocean equilibrated with core destined alloy, that we would have the problem of explaining why, not why Earth has the redox budget that it does, but how to get rid of what was initially an extremely oxidized mantle that would have descended from the magma. Okay, that previous slide was out of place. Now we'll go back to it. So I presented 3 hypotheses for the origin of the oxidized bulk silicate Earth. And the one on the right is the one that we affirm. It is entirely plausible that the oxidized budget of the entire accessible Earth was born from high pressure equilibration of silicate with core destined alloy in the magma ocean stage. That does not mean that there wasn't hydrogen escape that didn't contribute to it. It also does not mean that there wasn't an additional step of Bridgmanite crystallization leading to further oxidation in the deep mantle. It means that they're not necessary, that it all can be explained by the magma ocean. So the simple model would be something like this, that a deep magma ocean with metal raining down and destined for the core and having a mean pressure of equilibration in the realm of 30 to 50 GPa, which is what people infer based on siderophile element partitioning, that's where those numbers come from, can create an oxidized surface. There may be further, I don't mean surface, I mean can create an oxidized accessible or bulk silicator that translates later to an oxidized surface. Later hydrogen escape or later further manufacture of metal by Bridgmanite crystallization, possibly aided by a basal magma ocean to help the metal escape to the core, are possible but not required. Okay, so this was my template. Let's go back through it because these are my conclusions. What is the vigor history of redox balance exchange between the interior and exterior? Extremely vigorous. The Earth is exchanging its entire surface reservoir on a timescale of approximately 1 billion years, and is doing so with this conjugate reactions of carbonate coming out and ferric iron coming in, at least in the modern Earth. FO2 scaling and the magnitude origin of possible mantle secular evolution. If the mantle has evolved at all in FO2, not individual domains, but I mean average mantle has evolved in FO2 through geologic time, then the mass fluxes required for that are really large and something that are going to have to be faced. We can't simply say, oh, it's changed a little bit in oxygen fugacity. We're going to need to say there was some really large scale mass flux that has occurred that has to be realistic and plausible. And the origin of Earth's oxidative power, the bulk silicate redox budget, magma ocean, Bridgmanite crystallization, hydrogen escape, None of these are falsified, but the magma ocean turns out, it seems, based on the experimental data that we have, and we do need more experimental data, but based on the experimental data that we have, the magma ocean itself could have done all of it. And thanks for listening.
Thanks, Mark. This was great. This is a very cool talk. So we'll open up the floor for questions from participants. You can raise your hand, put it in the chat, and then we will call on you.
Thanks very much. Two things. First of all, you didn't say this, you hinted at it, but to me, the magma ocean hypothesis for segregating the metallic iron is much more attractive than the solid state Bridgmanite hypothesis, because no one has ever explained how you actually aggregate the nanophase iron that would be produced by solid state disproportionation and separate it from the mantle. That part has always been magic happens at the end of these papers on disproportionation. That's just a comment.
Thanks, Paul. Actually, you're amplifying something that I could have emphasized better, so I welcome the opportunity. That's true. The Bridgmanite crystallization is not just a chemical effect, but it requires a physical process of small amounts of iron or perhaps iron sulfide segregating from the proto-lower mantle. And that can be very difficult. On the other hand, something that I recently suggested in print that maybe nobody will notice, but maybe I can point to it, is one really excellent way to do that is a basal magma ocean, because then the nanophase iron metals can rain right through that and into the core. So if there was a basal magma ocean, that helps that hypothesis.
And my question is, does your point about the imbalance between the carrier of redox potential out of and into the mantle, one's carbon, one's iron, does that imply an elemental imbalance, that there's net carbon out and net iron flux in, and how long can you keep that up? Or does the redox potential get handed back from iron to carbon in the mantle, and so you can have this imbalance in who's carrying the redox potential without an elemental flux imbalance?
Yeah, this really gets to the coupling between the deep carbon cycle and the redox cycle, because I think that the evidence from the sedimentary record is that the carbonate reservoir has grown with time. And so in order for that to be the case, and also the oxidative reservoir has grown with time. In order for that to be the case, there can't be too much of an elemental imbalance. But in order to do it carefully, what one would need to do is to look at the fluxes of the conjugate redox pairs. So that would be how much reduced carbon is being subducted, how much ferrous iron is coming out and also being subducted. And so I think it's possible to do the conjugate work without a net flux of net elemental fluxes. But on the other hand, I believe that there are net elemental fluxes. There is a growth of the oxidative reservoir with time, and there is apparently a growth of the carbonate or of the carbon on the surface with time.
Dan, you can go ahead and unmute yourself and ask a question.
Marc, it was a great talk. So I have a question about your comments of using subset of the data set and not preferring the samples with many metal particles. Are you interpreting that as a sign of crystallization producing extra metallic iron? So you sort of reject those data points? I just want to learn about the criteria that you apply for the rejection of those data points.
We simply didn't analyze samples that had appreciable metal. Precipitated micro to nanometal. We did experiments where we thought we were analyzing clean glass. Our original experiments had this distributed metal, and the problem is, and Dan, you probably have a better perspective on this than I do, what's the origin of that metal? Is it created under the laser beam during heating, in which case it's a quasi-equilibrium phenomenon, or is it created during quench, in which case it is not an equilibrium phenomenon, and the melt prior to quench had that material dissolved in it. At those temperatures, we're talking about 4,000 K, I think both are plausible. And because of that, I mean, you may have an opinion that it's one or the other, but I would say that if you have experiments that have that, that your results depend on your assumptions. And if you can do experiments where you don't have the little metal precipitates, then you're in safer territory.
Right, right. My impression about this observation, I don't have a simple answer to this. And I've seen this metal precipitation quite often from laser heating, particularly related to the pyrolytic composition. So whether this is an equilibrium process or non-equilibrium process contaminated by laser heating is a big question. And so I'm personally sort of always concerned about reproducibility of this metal generation, whether that is really related to the type of process going on in the nature system, or it is really the process that is going on in the system, but it is relevant to our capability of resolving these small particles because we are getting better and better. And I feel like it's the latter because more we have higher resolution, we seem to identify these features more robustly. So let me, but it was great to hear from you about your experience.
Let me clarify that the highest resolution images that I showed were very high resolution SEM images. There was a 100 nanometer scale bar there, and we cannot see metal down to what seems to be, tens of nanometers. On the other hand, we do not have TEM images of those classes, and there could be something on a much finer scale that we haven't yet seen.
Yeah, I have seen down to 10-ish nanometers in TEM. So yes, they can be very small. And I was always concerned about whether it exists at this even smaller scale, but we didn't notice it because of the difficulty of sample preparation and recovery and polishing and all that stuff. But thank you so much.
Okay, Dave Walker has typed a question and let me read it. It says, my question is, are you ready to exclude the late veneer as having much to do with mantle redox, given that you require vast material fluxes to do the job of shifting the mantle? No, I won't dismiss the late veneer. The thing about the late veneer is that unless it's really oxidized, purely CI chondrite, then the late veneer comes with metal and it's a reducing contribution. If I did a calculation in this paper that I published last year that said if it's 80% non-carbonaceous chondrites and 20% pure CI, then it's neutral. And so the late veneer has the potential to be a very significant added reductant to this process, which, in order to explain what we actually have in terms of Earth's redox budget, means that we would need more oxidized material originating from the magma ocean, originating from bridgemanite disproportionation, originating from water disproportionation and hydrogen loss, or some combination. So it's definitely a player. It makes the problem harder. And then Daniel Hummer also typed a comment. When we talk about the mantle redox state and changes, we have to remember that current evidence suggests that there are actually at least 2 different mantle reservoirs. I won't write the detail, but he's pointing out that both in terms of the LSVPs and the rest of the mantle, could some of the redox dynamics that we see through Earth's history be due to mixing of these materials or LLSVP material leaking up to the surface, et cetera? Is this idea crazy? No, it's not crazy. One of the things that we have to wrestle with is that a lot of our record for the modern mantle comes from periddotites and from mid-ocean ridge basalts, and we're beginning to get evidence from oceanic island basalts that they come from more oxidized sources. And the question would be, what do they sample and what volumes do they represent? Most of the evidence from oceanic island basalt seems to indicate recycling. And of course, I said that there's not necessarily a big net secular increase, but certainly recycling has created oxidized and reduced domains in different parts of the mantle. So the possibility that there's parts of the mantle that are hiding that are more oxidized than what we have from sort of typical mid-ocean ridge basalt and periddotite mantle is feasible.
Okay, and Ben, you can go ahead and unmute yourself. We'll take this one last question.
Yeah, I was waiting to see if we had time. Hey, Mark, great
Hey,
talk.
Ben.
I got the MSA talk reminder and figured I'd watch this over lunch. So, as someone coming from a tectonics community and from the surface down, and worked a lot in Archean, what my question is basically, say plate tectonic processes weren't as active in Neo-Mesoarchean and older. A lot of people have proposed things like critical mantle overturn events and things. How would variable mantle mixing and dynamics through Earth's history change your mass balance models? Is the short part of the question.
Yeah, the simplest answer that I can give you is that my mass balances are based on what we observe today.
Gotcha.
Certainly on the surface and also in terms of the mantle, that's really the modern upper mantle that I'm talking about.
Yeah.
So in terms of mass balances, if there are earlier things that are hiding, or if there were earlier things that have mixed in, then I can infer it based on these sort of model-dependent things that I kind of referred to, but I can't completely control for them.
Yeah, that's great. And at least it seems like your approach could be potentially applied to explore variations and mixing through time and whatnot, right? Because you could use a similar framework to sort of explore how fluxes might have changed, if I understand.
Right. What I would like is when geochemists say that they are talking about a mantle source that is 1 log unit more oxidized or 1 log unit more reduced, that they then say that they're talking about a mantle that has an RB that is increased by whatever it is at those particular oxygen fugacities by a large amount, 30%, 50%, something like that. And give us information not just about chemical potentials, but about the mass fluxes that are required to explain the changes in chemical potentials.
Yeah, I gotcha. Okay. Yeah, very interesting. Thanks, Mark. Enjoyed it. Cheers.
All right, thank you, Mark, so much. Thank you, everybody, for joining us today. We appreciate it. We'll see you back here in about a month for our next seminar. Let's give let's give Mark another last round of virtual applause. Thank you so much.